Hello everyone, thank you very much for joining me today. My name is Iman and I'm here to present our work around encrypted traffic classification on behalf of our team in University of Waterloo and Orange Labs, France. Traffic classification is the task of categorizing a network flow, packet, or endpoint into predefined classes. And it's of utmost importance for many network management operations, especially for the ISPs, ranging from capacity planning and resource provisioning to telemetry, or as we call it, volumetry and monitoring, ensuring quality of service guarantees, anomaly detection and cybersecurity, targeted marketing, that's an important one, and business strategies, and more. Thus, there are many different ways, many different levels, as you might call them, in which we can classify our traffic. So, for example, we might be looking for finding different kinds of services at the high level, for example, video, social, gaming, etc., or specific applications such as Netflix, YouTube, Amazon, so on and so forth. This allows us to gain insight into how the users are spending their time online and how we can enhance their experience. There are many different use cases as well. So, for example, we might want to know about the quality of services that the users are experiencing, the cybersecurity aspects, for example, for the next generation IDS systems. We might even want to have visibility into the actual contents that is being transmitted in our network, for example, actual videos, actual movies. However, in this project, we were mostly focused on service and application level classification, primarily because of the high industry interest. Machine learning is evidently a very powerful tool for traffic classification, and as the complexity of the task grows, the only feasible approach is to leverage the data to classify traffic. Today, to ensure the privacy and security of our users, our network's traffic is using encryption more and more prevalently. While 20 years ago a large portion of our traffic was transmitted out in the clear, today encryption has become a de facto standard in most ubiquitous web protocols. QUIC and HTTP2 are very good examples of this development. They have been around for a few years now, and aside from making TLS encryption a de facto and bringing it to the transport layer in the case of QUIC, these protocols introduce new and exciting features as well, such as session multiplexing, header compression, server push request pipelining, etc., etc., which all adds to the challenges and complexities of web traffic classification. It is fairly obvious that encryption is a big deal for traffic classification. We've seen approaches with higher than 95% accuracy in plain text traffic completely degenerating when applied to encrypted traffic. This is significant for traffic classification. We need to change the way that we think about encrypted traffic and separate it from regular use cases. So let's go through a very brief recap of how this field developed in the first place. In the early 2000s, the area's focus was mostly revolving around distinguishing between different protocols, such as DNS, HTTP, SMTP, SSH, etc. And this was performed based on the flow statistics that were gathered by standard flow meters, such as NetFlow. And these features are mostly things like the entire duration, number of packets, average packet length, average inter-arrival times, TCP flags, things like that. And the features used in these works were often fed to traditional machine learning algorithms such as the naive Bayes method, decision trees, more recently SVMs. However, the field's attention soon went to more interesting, challenging, and practical domains such as detecting encrypted and unconventional applications such as Skype or Tor, which do not operate on fixed port numbers, and detecting them is a genuine problem. However, the major breakthrough in this field came from the advancements in deep learning, which changed the area's landscape. So we saw a lot of research efforts using deep neural networks similar to those used in more conventional machine learning areas such as computer vision for traffic classification. A lot of these works follow the idea of presenting the data in its rawest form to the model and letting it figure out what features are important. And the rawest form of traffic is of course going down to the actual bytes of the flows and packets, which is what most of these methods actually do. And it turned out that neural networks such as one-dimensional convolutional neural networks, CNNs, and also long short-term memory layers, LSTMs, etc., do have a lot of promise for traffic classification. This reinforced this analogy between images and traffic. Can we think of traffic as a one-dimensional image and simply train based on that? Well, it's more complicated than that. Among other issues, encrypted traffic is not exactly like an image. It's more like an image where all of it, but a very small portion of it in the corner is obfuscated. Kind of like those fuzzy black and white pictures, black and white noise in old TVs when I was a kid. So this is a major inspiration of our work. We need to apply some sort of domain knowledge and change the way that we deal with encrypted traffic. So there are multiple considerations regarding the state of the art that motivate our approach and compel us to design our own framework. We already mentioned encryption. Non-encrypted traffic can be deterministically classified in theory in most use cases at a very low cost using simple header matching. So training deep learning models running on hundreds of GPU cores to do that is sort of pointless. However, we did identify other issues in the state of the art as well. So for example, we've seen this trend of gerrymandering the labels and classes where you have, for example, YouTube, which is a specific application, email, which is a broad category of services, and DNS, which is a protocol, all at the same time, which is not even the same level of granularity. And that is even in more prominent works. So this might produce questionable results. There are also protocol-specific approaches that are being used that can break down easily even with minor updates to the protocol. However, most crucially, it is important to ask ourselves, what is it that our deep models are really learning? Is it useful? So for example, in a post-hoc analysis of one of the more prominent works in this area, we saw that the model, first of all, the model that is 96% accurate overall, it's only 75% accurate on the encrypted HTTPS part of their dataset. It was also shown that if the server name indication, the SNI extension of the handshake was occluded, the model would basically deteriorate into 30-something% accuracy and become useless. The SNI is a TLS record that sends the server name out in the clear. So for example, if you look at your traffic dump, you would notice among all the seemingly random bytes, you would notice a plain text part saying www. For example, google.com. So it is safe to say that the model is just learning to look for that plain text part, match it against the lookup table that is learning, and do that classification based on that, which is very alarming. We call these features canary features. They give away the identity of the server by themselves out in the clear in plain text. So you might very reasonably ask, what's wrong with that? We want to do classification and we can use all the help that we can get. First, these records are not going to be around forever. The encrypted SNI, for example, is already on its way, and these protocols are evolving to protect user privacy more and more each day. But however, more fundamentally, using a deep learning model for learning such a simple logic is sort of like using a shotgun to open a can of soup. We can just implement the same logic in a few lines of code instead. Thus, we need general frameworks that can learn actual patterns based on the nature of the traffic, especially the encryption agnostic aspects of the traffic. And we need frameworks that are applicable to all or at least most encrypted protocols, not a specific version of a specific protocol, in order to adapt to the evolution. To achieve that, we were inspired by some of the more fringe areas of the traffic classification literature that view the traffic as a time series of packet sizes and inter-arrival times, the traffic shape, so to speak. So I've seen, for example, in one of them, the traffic shape used along with features extracted by domain experts from the handshake for detecting malware. We also seen in another application, interestingly, that, for example, the traffic shape can even be used for fingerprinting what exact video a user is watching over YouTube or Netflix. So one might argue that streaming traffic is peculiar because the more action you have on the screen, there are more traffic bursts. And based on that, you can fingerprint a video and use it for classification. However, it's natural to ask whether the same strategy can be used for example, service and application level classification. So we started incorporating similar approaches into our framework, and as it turns out, traffic shape can be used in service and application level classification as well. The differences between some classes are obvious. So by the way, this is the traffic shape average for each class in our real-world data set, which we will cover later. But for example, even for humans, by eyeballing it, you can detect some of the more obvious ones, such as streaming traffic because of its bursty nature. And even in cases where the flows are relatively similar between two classes, there are subtle patterns that might be difficult to detect for humans. However, good news is that deep learning models are pretty good at detecting subtle patterns. Based on these observations, we propose a general feature model for encrypted traffic comprised of three parts. First, we have raw handshake bytes. Second, we have the flow shape time series that we covered earlier. And third, we have the good old-fashioned flow statistics. So let's go through them one by one. First of all, we must be careful with how we use raw features. When 90-something% of your traffic is encrypted, it makes little sense to feed the entire encrypted bytes to the machine learning model. That's essentially tantamount to designing an attack on the encryption algorithm, such as AES, and well, good luck with that. Thus, we only incorporate the handshake in our features, and we also remove the SNI and TLS ciphers, the canary feature, so to speak, because we want to study the behavior of the model without having access to those obvious features. Second, we have an emphasis on the flow shape, and these are kind of our favorites because protocols may evolve in different ways. More and more parts of the traffic will be encrypted. However, the traffic shape, the time series of packet sizes, directions, and timing, that will always be there. They can't take that away from us. And it's extremely costly to obfuscate these aspects of the traffic because you would need redundancy and latency to do that. And it's highly unlikely to be justified for any ubiquitous web protocols because there simply isn't enough motivation to do that. Lastly, we still like the flow statistics. They have been around for more than 2 decades, and they can help the model by providing it the most obvious features and letting the other 2 legs focus on the more complex features. And it's also useful for maintaining generalizability in our framework because there are many features that are handpicked by domain experts for certain use cases, and it's good to have a place for incorporating them into our framework as well. And we believe that this is a much better fit for encrypted traffic than the conventional methods. The architecture of our model reflects the feature engineering shown before. To get to this, we did a lot of experiments with different layers, architectures, and hyperparameter values, and we did a lot of trial and error experiments. The 3 parts of the model are fed separately to the 3 different legs of the model. So the initial layers are different. For the handshake, as we've seen before in the relevant literature, it turns out that convolutional layers are a very good fit. And these layers are repeated and followed by max pooling layers and then convolutions, again max pooling, sort of like simple computer vision models. And we did experiment with other things as well. So for example, we tried Fourier transform, we tried 2-dimensional convolutional networks, and as shown in some of the other works in this area, 1-dimensional CNNs did produce the best results in our experiment. The layers processing the flow time series need to be able to process complex fine-grained or coarse-grained patterns, and that's why it turns out stacked bidirectional LSTM layers are a very good fit for this, despite being quite expensive to train. They do produce very good results. And lastly, the flow statistics are processed using regular fully connected layers because there's no sequentiality to them. The results of these initial layers are concatenated and then passed through additional fully connected layers. These are very important too, and they produce a probability distribution in the final softmax layer, which is the case for most neural network classifiers. For evaluations, we used the real-world dataset gathered by Orange from their mobile networks in France, and we really cared about using real-world and non-synthetic data because in the past we had seen that synthetic datasets are not very representative for real-world traffic. And that's actually one of the shortcomings of many works in this area, the fact that they use synthetic datasets. We were able to label around 1/3 of these real-world TLS flows based on the server name indication, based on their SNI, which is of course later on matched for the actual training. And we use them for labeling at both service and application level, that is coarse-grained and fine-grained. We also use the ALPN extension. We extract some metadata, including the next protocol negotiations, to keep track of the HTTP version, for example, in the evaluations. We designed our pre-processing pipeline using the Apache Spark ecosystem in order to ensure horizontal scalability. And the final output is batches of binary vector files that are ready to be used by all standard machine learning libraries. After 40 epochs of training, our model achieves 95.56% accuracy and 95.5% weighted average F1, which is pretty high for encrypted traffic. It is fairly stable across all the classes, with the F1 being higher than 94% in all of them. And as we predicted earlier, the flow shape by itself contributes a lot to the model. Actually, if the flow shape is used alone, and fed to the stacked LSTM layers described earlier, it achieves 86.71% accuracy, and that means if we dispose of the other two legs and use the LSTM layers only. Which is not bad considering how low level and simple it is, but it is when combined with the other two legs that is actually shining and showing its potential, because it compensates for the parts that the other two legs, especially the raw handshake bytes, make mistakes in. When compared to the counterpart CNN model from the UC Davis team, which is one of the more prominent works in this area and one of the more successful ones, the advantages are clear. The CNN model, relying on only raw features, overfits very fast to the data and gets stuck at around 91% accuracy, while in our proposed model, the training and validation accuracies converge, and the model is very well generalized. And in the end, the model has around 50% fewer false predictions, which is a significant margin. The only downside, however, is that the training time is much higher than our competitors because of the stacked LSTM layers that add a lot of computational complexity. To address that, we experiment with changing the flow time series side of the model from the stacked LSTM layers to convolutional neural networks as well. And while the accuracy wouldn't be as high as it was before, it would still be a 40% advantage over our competitors, while the training time would be in the same ballpark. So essentially this way we can set the trade-off between the final accuracy and the training complexity. Another thing to notice here is that the traditional baseline for this experiment is at around 80% using decision trees. And that means that that's around 4 times the number of false predictions, and that means that it's not even in the same order of magnitude. We also showcased that our approach can adapt to different granularities of the classification. We picked 19 applications with sufficiently large amount of data in our dataset for training and trained our model for the purpose of detecting those specific applications. So for example, here we have Twitter, Snapchat, Gmail, specific applications. And despite the obfuscation of the SNI fields and cipher values, which are particularly helpful for application detection, we achieve higher than 97% accuracy in this closed word problem. Lastly, we also showcased how the trained model performs on different web protocols. While the speculations about HTTP2 being more challenging to classify is true, as the model is around 98% accurate on HTTP1, it is still pretty accurate on HTTP2 as well. Like it is lower, it's at around 95% for HTTP2, but it's still, compared to the state of the art, is pretty good. And something else to note here is that for the flows that did have the ALPN extensions, that is the next protocol negotiation, which we use to determine the underlying protocol, the accuracy is much higher for the flows that do have this information compared to the ones that don't. And we attribute that to these flows being captured in the beginning of the user session compared to these ones that are probably intercepted in the middle. And that also shows that there is more information in the beginning of the user session compared to the other parts. We also evaluated our model on the quick data set that was provided by the UC Davis team. And here it's a simpler data set because there's only 5 applications, and that is because Google is the primary supporter of the quick protocol. And here we can see that the model achieves a very good result, 99.37% accuracy, which is higher than the best accuracy reported by the authors, and that shows that we can adapt to other protocols as well. In future works, we propose the study of the transferability, the transfer learning, and domain adaptation of traffic classification models. So for example, can a model trained for a certain task be used for another task, for example, with a different granularity by making minor adjustments to the model, for example, the final layers? And also the domain adaptation, for example, can we have a model trained in certain conditions used for adjusted for other conditions? We are also interested in the fact that how network conditions do affect the accuracy of the model. It's also interesting to know about how effective adversarial attacks are on traffic classification models, and not just adversarial attacks, all machine learning attacks, for example, model inversion and all of that, how vulnerable in terms of privacy would a model be, for example, in a federated learning. We need to catch up essentially to the machine learning community, to the hot topics in the ML community, and bring it to the traffic classification. It is also useful to keep experimenting with different architectures such as attention networks. Our preliminary experiments didn't show a lot of promise for these particular networks, but it's important to keep exploring. So thank you very much for your attention. I would be happy to connect through email, and have a great day.